Hello everyone. We're going to continue now our discussion. So this is the last slide I have presented now. So we now proceed with problem 3. Assuming specific weight of air to be constant, 12 newtons per cubic meter. What is the approximate height of a mountain if a mercury barometer at the base of the mountain reads 654 millimeters and at the same instant another barometer at the top of the mountain reads 480 millimeters. Okay, let us analyze the problem. So we have here a specific weight of air is constant at 12 newtons per cubic meter. Okay, so in this case, we have this mountain. So we are going to determine the approximate height of it now. So what will be the approximate height of this mountain if we have a mercury barometer at the base of the mountain reads 654 millimeters of mercury. Okay, this is at the base. Okay, at the same instant, another barometer at the top of the mountain reads 480 millimeters of mercury. Okay, and air is assumed to be constant at 12 newtons per cubic meter. Now, given this condition, what will now be the approximate height of the mountain? So let us solve the problem. Solution to the problem, recall this formula, no? So P2 equals P1 plus unit weight times age. Now in this case, we have here P2 is the pressure, no? Which is higher than P1, no? Pressure higher than P1. And we are expecting that the pressure at the base is higher than the pressure at the top. Okay? That's why in our formula, the base represents P sub 2 and the pressure at the top represents P sub 1. Okay? So with that, we have unit weight to be unit weight of air and height h be the height of the mountain. Okay? So take note that this formula, no, can be expressed in terms of absolute form. So the pressure at the base, okay, since this is the reading, this is the atmospheric pressure, okay, 654 millimeters mercury, that will now be converted to absolute pressure of 654 millimeters mercury also. Okay, same as the pressure at the top, we have 480 millimeters of mercury, so that will also be our pressure, no? Our absolute pressure, okay, at the top. So in this case, we are interested in determining the height of the mountain. So in this case, we subtract the pressure at the base, absolute, minus the pressure at the top, absolute, all over the unit weight of air. And recall that we have here the barometer, okay? And in this barometer, this is the height of mercury. And the formula in finding the atmospheric pressure is simply equal to the product of the unit weight of mercury and the height of mercury. Okay, so that is simply the formula. And take note that this is considered perfect vacuum. No, this is considered perfect vacuum. If it is a perfect vacuum, the absolute pressure is zero for a perfect vacuum. No. Next we have, so in this case, the height of Mercury, when multiplied by the specific wave, corresponds to the atmospheric pressure, which is also the absolute pressure, no? The corresponding absolute pressure, no? The absolute pressure of the atmosphere, no? At the base and at the top, okay? So in this case, the formula for finding the absolute pressure is equals to the gauge pressure and plus the atmospheric pressure. Since the gauge pressure is zero, no? For atmospheric pressure, the gauge pressure is zero. Therefore, the atmospheric pressure is simply equal to the absolute pressure. No? The absolute pressure now is simply the product of the unit weight of mercury and the height of mercury. Okay? Now, the absolute pressure is simplified as gamma H, no? For mercury. So in here, uh, we have the absolute pressure at the base, that is simply the unit weight of mercury, the height of mercury at the base. Okay, that is already in absolute form. And then the pressure at the top, unit weight of mercury, height of mercury at the top. Okay, then we divide it by the unit weight of air. Okay, now, so we can factor out the unit weight of air. Okay, and what is left inside is the height of mercury at the base, height of mercury at the top. Then we divide it by the unit weight of air. Okay, so in this case, the unit weight of mercury, okay, is simply the product of the specific gravity of mercury and the unit weight of water at 4 degrees Celsius. No? Because recall that the specific gravity is the unit weight of the substance over the unit weight of water at 4 degrees Celsius. So, if we multiply the specific gravity and the unit weight of water at 4 degrees Celsius, we can obtain the unit weight of that substance. And since our substance is mercury, so we just multiply the specific gravity of mercury and the unit weight of water at 4 degrees Celsius. Okay? So that we can obtain the unit weight of mercury. So unit weight of mercury now is specific gravity of mercury times unit weight of water at 4 degrees Celsius. Alright, so we continue. So the specific gravity of mercury. So in the problem, it was not mentioned the specific gravity of mercury. It is understood now that the specific gravity of mercury is equal to 13.6. Okay? The unit weight of water at 4 degrees Celsius, okay, always remember that it is 9.81 kilonewton per cubic meter. Okay? It is also 62.4 pounds per cubic foot. Okay? 62.4 pounds per cubic foot. So in this case, we use the SI unit. Okay? So we have here height of mercury at the base minus height of mercury at the top. So we have 654 millimeters of mercury at the base minus 480 millimeters of mercury at the top. Okay, and then we should be consistent with our units. So for every millimeter, that is 10 to the negative 3 meter. Okay, and then for every kilonewton, that is 10 cube newton. No, so cancel. Okay, so what is left is, so we have here 12 newton per cubic meter. This can also be cancelled. Okay, then we have per cubic meter cancel. So what is left is meter. So the height now of the mountain is expressed in meter. And the answer is 1,935 meters. Okay? Alright, there's an alternative solution to this problem. Recall that P2 equals P1 plus gamma H. Okay, the pressure at the base equals to the pressure at the top plus unit weight of air times H. Okay, so in absolute form, okay, we have this formula. And then we subtract the pressure at the top from the pressure at the base. Then we divide it by the unit weight of air to get the approximated height. Now, this is, we know that this is 654 millimeters of mercury. This is for 80. Then we have unit weight of air at 12 newtons per cubic meter. So we can able to multiply by this conversion. So recall the conversion that one atmosphere, no, 1 atmosphere is equals to 760 millimeters of mercury, which is also equals to 101,325 Pascal. And that is Newton per square meter. No? That is Newton per square meter. Okay? That's why we have this conversion. This is 180 m, this is 180 m. So, so that we can cancel millimeters of mercury. Okay? So we have 760 millimeters mercury corresponding to 101,325 Newton per square meter. So Newton and Newton will cancel. So what is left? We have 1 over square meter all over 1 over cubic meter. And this is now 1 over square meter times cubic meter over 1. No? Times cubic meter over 1. Okay? So that's why we have cubic meter over square meter. We have meter. Okay? So the unit now is meter. So we have 1,933 meters. Okay? So this is an alternative solution. So there is slight discrepancy. Our previous answer is 1,935 meters. This is 1,933 meters. Actually, this will get nearer if we consider the unit weight of water at 4 degrees Celsius. Actually, if we consider 3 decimal places, this is 9.807 kilonewtons per cubic meter. Okay? So, if we consider that, it is nearer to our answer of 1,933 meters. No? I think it's 1,934. We will get 1,934. Well, it's just okay for as long as the solution is correct. No, that will be credited. No? So we can now proceed. So problem number 4. If the atmospheric pressure is 95.7 kPa and the gauge attached to the tank reads 188 millimeters mercury vacuum, find the absolute pressure within the tank. So we have here the atmospheric pressure of 95.7 kPa. And there is a gauge attached to the tank, no? Measuring gauge pressure, the reading is 188 millimeters vacuum. Okay? So 188 millimeters vacuum. So that will correspond to a gauge pressure of negative 188 millimeters mercury. No? It's because recall that vacuum pressure is negative gauge pressure. Okay? So we are to determine now the absolute pressure corresponding to 188 millimeters mercury vacuum. What is that pressure in absolute form? Solution: recall the formula. To find the absolute pressure, we add the gauge and the atmospheric pressures. And also recall that in thermodynamics, this was discussed, maybe it was discussed, that the gauge pressure is equals to negative of the vacuum pressure. No? And with that, we can now replace the gauge pressure here by the negative of the vacuum pressure. And this will now be our equation. No? And with that, we have negative 188 millimeters mercury. No? And then for every 760 millimeters mercury, there are 101.325 kilopascal. So this will be cancelled. And then the atmospheric pressure is 95.7 kilopascal. Okay? And we will have an answer of 70.64 kPa. So that is our answer for the absolute pressure. Okay? Or you can write 70.64 kPa. Okay? So A for absolute. Okay? kPa. Kilopascal absolute. Now, let us study this topic. Pressure below layers of different fluids. No? So if we consider here liquid 3, and above liquid 3, there's another liquid 2. And above liquid 2, there's another liquid 1. Okay? And above liquid 1, there's air. Okay? This is now our tank. A tank composing of air, liquid 1, liquid 2, and liquid 3. So as you notice, these are homogeneous fluids. No? There are certain substances when combined, no, will not mix, no? They will not there will not they will not be uh, one substance will not uh, mix with another substance. They remain homogeneous, no? They remain homogeneous. Okay? So liquids which are homogeneous, like water and oil. If you mix water and oil will separate from water. Okay? Oil will separate from water. No? So, in this case, so let's consider the height of the liquid, VH1, the height of liquid 2, VH2, and the height of liquid 3, VH sub 3. Now, there's a pressure at the bottom. Okay? We have a gauge meter or gauge meter, okay, capable of measuring gauge pressure. Now consider the closed tank shown below, filled with liquids of different densities and with air at the top under a gauge pressure of P sub A. So there is gauge pressure here of P sub A, no? So at this portion, so we have P sub A, no? So we have P sub A, okay? So which is air pressure, no? At the interface of liquid to air, okay? So the pressure at the bottom can be obtained by adding the air pressure, no? So the air pressure, okay? So the air pressure plus the summation of the product of the unit weight of a certain liquid and the height, no, of such liquid. So we will sum all of those liquids, no? Sum all of those product with respect to liquids. Okay? So in that case, since we have three liquids to consider, so we considered the pressure, the air pressure, PA, then we consider also the product of the unit weight of liquid 1 and the height, no? Same as the unit weight of liquid 2 and the height, okay? And then unit weight of liquid 3 and then the height. So adding all of those, no? Okay, so let's answer a problem with regard to this topic. So here's the problem. An open tank contains 5.7 meters of water covered with 2.8 meters of kerosene, having a unit weight of 8 kilonewtons per cubic meter. If the diameter of the tank is 1 meter, find letter A, pressure at the interface of water to kerosene. Letter B, pressure at the bottom of the tank. And C, total force at the bottom of the tank. So let us analyze the problem. So given we have an open tank, okay, contains 5.7 meters of water. So let's say this is water, okay, and the height of which is 5.7 meters. So we have 5.7 meters of water covered with 2.8 meters of kerosene. Okay, so we have kerosene with a height of 2.8 meters, having a unit weight of 8 kilonewton per cubic meter. So this kerosene has a unit weight of 8 kilonewtons per cubic meter. And then, this is an open tank. Okay? So, an open tank. So, this is open. The tank is open. Now, we considered also the diameter of the tank. It is indicated to be 1 meter. Okay, the diameter of the tank is 1 meter. Find the following. The pressure at the interface of water to kerosene. So the pressure at the interface of water to kerosene, we're going to identify that. Okay? Then the pressure at the bottom of the tank. So the pressure at the bottom of the tank. And then the total force at the bottom of the tank. So we have the total force at the bottom of the tank. So because there's pressure at the bottom, there is the corresponding force. No? So let's analyze now. Solution for letter A. Recall the formula P sub 2 is equals to P sub 1 plus unit weight of the substance times the height. So in this case, so we consider gauge pressures. Okay, P2 and P1 in gauge. No? So we have, so the pressure P2, no? In here we have pressure P2 is the pressure of the interface of water to kerosene. Okay, what's that gauge pressure at the interface of water to kerosene? And then P1 is the pressure at the interface of kerosene and air. No? Because above kerosene is air. So what's that pressure at the interface of kerosene and air? Okay, so since this is gauge pressure, so it will now be 0. Okay, it will now be 0. Then we add the unit weight of kerosene, okay, multiplied by the height of kerosene. So in here, the pressure at the interface of water to kerosene is now equal to 0 plus 8 kilonewtons per cubic meter multiplied by 2.8 meters. And we will get an answer of 22.4 kilopascal. No? And that is 22.4 kilopascal gauge. No? 22.4 kilopascal gauge. So that is the pressure at the interface of water to kerosene. No? Applying this formula. Okay? So we have, so this is the, what formula is this? The pressure variation formula. Okay? So letter B, we are interested with finding the pressure at the bottom. And if we are interested in finding the pressure at the bottom, okay, recall the formula to find the pressure at the bottom. That is the pressure at the top, since at the top is air. The pressure of air at the top, okay, plus the summation of the product of the specific weight of a substance to its height. No? Now, since we have three fluids involved, we have air, kerosene, and water. So the pressure of air, no, air pressure, plus unit weight of kerosene times the height of kerosene, plus unit weight of water times the height of water. Okay? And we consider them to be in gauge. No? So pressure at the bottom, gauge, pressure of the gauge. Okay, so pressure at the bottom, that's P sub B. Pressure of air, okay, so that is at the interface of kerosene to air, which is 0. No? The interface of kerosene to air. So PA here is the same as the pressure at the interface of kerosene to air. Plus Y sub 1, H sub 1. So our first liquid is kerosene. So that is gamma sub K times H sub K. Plus the second substance is water. And the temperature of water was not mentioned, so our assumption is that water is at 4 degrees Celsius. And in that case, the unit weight of water at 4 degrees Celsius which is the standard, will now be utilized, no? So multiply by the height of water at 4 degrees Celsius also, no? So in this case, the gauge pressure at the bottom, so we have the gauge pressure at the interface of kerosene to air, 0, plus the unit weight of kerosene is 8 kilonewton per cubic meter. The height of kerosene is 2.8 meters plus 9.81 kilonewton per cubic meter. That's the unit weight of water at 4 degrees Celsius. And then the height of water in the given figure is 5.7 meters. No? So we have our answer of 78.32 kilopascal. And that is 78.32 kilopascal gauge. No? Now, so that's the pressure at the bottom. What will now be the force at the bottom of the tank? So the force at the bottom of the tank, we consider the pressure at the bottom, which is 78.32 kilopascal gauge. So since there is pressure, there will now be a force corresponding, no? A corresponding force. So that force is a normal force, okay? And the diameter of the tank is 1 meter, okay? So this is now the diameter of the tank. And since the diameter is considered, so therefore this is circular. And since this is circular, we have a circular area, okay? And recall that the pressure is equals to the force over area, no? Force over area. Or sometimes it's an infinitesimal force over an infinitesimal area. So if this is a certain area and there is force acting on that area which is infinitesimal, and the pressure now is simply dF over dA, no? So at any point in this area, okay, the pressure is constant. The pressure is 78.32 kilopascal gauge, no? So with that, we have the pressure F over A is now, we can now solve for the force, which is the product of the pressure and the area. So the force at the bottom of the tank is now equal to the product at the bottom of the product of the pressure at the bottom of the tank, P sub B, multiplied by the area of the tank, which is at the bottom, no? Area of the tank at the bottom. So with that, we consider, so we have this formula, FB equals PBA. So we know that the area of a circle is pi over 4d squared, right? So pi over 4d squared. And the pressure at the bottom is 78.32 kilopascal gauge. And that is now 78.32 kilonewton per square meter. Okay? And the diameter is 1 meter. Okay? So we will now have an answer of 61.51 kilonewtons. But there's an alternative solution to that, no? So we have here, we consider kerosene and water, the weight of kerosene and the weight of water at 4 degrees Celsius. Okay, if we add the two, weight of kerosene, no, we have weight of kerosene, then the weight of water at 4 degrees Celsius, that corresponds to FB, the force at the bottom of the tank, no? Okay, so recall that the specific weight of the substance is equals to the weight over volume, no? The weight of the substance over its volume, no? And the weight of the substance is simply the product now of the specific weight of the substance and its volume. So in that case, the weight of kerosene is now expressed in terms of specific weight and volume. Okay? Same as the weight of water, specific weight and volume. So the temperature of water was not mentioned. Again, it will be assumed to be at 4 degrees Celsius. So F sub B, that is equals to unit weight of kerosene, the volume of kerosene, okay, the volume of kerosene. So this is circular, right? So we have area of the tank multiplied by the height of kerosene. No? The area of the tank multiplied by the height of kerosene. So that's the volume of kerosene in the tank. Same as for water. Okay? The area at the bottom multiplied by the height, 5.7 meter. Okay? Okay, we can factor out A. This will now be the simplification. Okay? And the area A is pi over 4D squared. Okay? And we have now, we can substitute pi over 4, 1 meter squared. Unit weight of kerosene, 8 kilonewton per cubic meter. Height of kerosene, 2.8 meters. Plus 9.81 kilonewton per cubic meter. This is for water. Multiplied by 5.7 meters, which is the height of water at 4 degrees Celsius. And we will get the same answer of 61.51 kilonewton. No? So 61.51 kilonewtons. Alright, so we can now proceed. Alright, let's study pressure head of a liquid. No? So pressure head, when we talk about pressure head, this is the height h of a column of homogeneous liquid of unit weight gamma that will produce an intensity of pressure P. No? So consider this vessel. No? So we have here the height of the liquid in this vessel. Okay, and we have here the specific weight of the substance inside this container. No? And there is now measured pressure at the bottom. Now, the height of the substance inside the vessel can be obtained by dividing the pressure at the bottom, which is P, to its specific weight. Simply as that. No? So, provided that the gauge pressure at the interface of the liquid and air, no, or liquid to air interface is zero. No, the gauge pressure is zero. So we note that h here is the height of a column of homogeneous liquid. So this is homogeneous, and we call it as pressure head. P is the pressure, gamma is the specific weight. So this is simply the pressure head formula. Okay, H equals P over gamma. So we have here pressure head conversions. So pressure head conversion, for example, if we have this column of liquid, okay, we have the specific weight of this liquid and the pressure at the bottom. So this is the formula for the pressure head, P over gamma sub 1. Okay, the pressure at the interface of liquid 1 to air is 0 for its gauge pressure. Then we consider another substance, okay, with the height h sub 2. Okay, specific weight is by gamma sub 2. Okay, that produces the same pressure as the first liquid. Okay, so the pressure head is equals to P over gamma sub 2. Okay, so take note that producing the same pressure, but the pressure heads are not the same. They're different because their specific weight are not the same. No, the specific weight of the substances are not equal. So same. So this formula is correct provided that the pressure at the interface of liquid 2 to air, no, is equals to 0 gauge pressure. No, 0 gauge pressure. So take note that the pressure of liquid 2 is the same as the pressure of liquid 1. And with that, no, the pressure is simply the product of the specific weight of the substance to its height. No? So we have H2 gamma 2 is equals to P. Okay? P1 same gamma 1 times H1. So we have now this formula. To find the height of liquid 2, we simply multiply the specific weight of liquid 1 to its height. Then we divide it by the specific weight of liquid 2. Okay? So that's the formula. Recall also that the specific weight of the substance can be obtained by multiplying the density of the substance to specific to acceleration due to gravity g. No? So h sub 2 is now equal to, so specific weight is gamma rho times g, density times acceleration due to gravity. Okay, so rho 1 g, okay, that is gamma 1 times h1 all over gamma sub 2, that is density rho 2 times g. So this will now be rho 1 h1 over rho 2. Recall the specific gravity of a substance is equals to the specific weight of the substance to the specific weight of water at 4 degrees Celsius. So that's the formula. And the specific weight now of the substance can be obtained when we multiply the specific gravity of the substance to the specific weight of water at 4 degrees Celsius. So in this case, so we can replace gamma sub 1. Okay, so we can replace gamma sub 1 here by this one. Okay, so if this is gamma sub 1, this is SG1. So that's why we have gamma sub 1 is SG1 unit weight of water at 4 degrees Celsius. Okay, times H1. Same as in the denominator, okay, we have the specific gravity of liquid 2, no? The specific gravity of liquid 2, okay, equal to the specific gravity of liquid 2 times unit weight of water at 4 degrees Celsius. Okay, specific weight of liquid 2 equals specific gravity of liquid 2 times unit weight of water at 4 degrees Celsius. So this can now be replaced by Sg sub 2 unit weight of water at 4 degrees Celsius. So we have this one. Okay, and this will now be the simplified form. So we can eliminate this one. Okay, so Sg1 H1 all over Sg2. Okay, so that's the formula. No, in converting the height of liquid 1 to height of liquid 2. So here's the problem. If the pressure head in a tank of oil, the specific gravity equals to 0.80 is 173 feet, determine the equivalent height in meters of water. Letter A, meters of water, and B, centimeters of mercury. No? So given we have this substance which is oil, okay, with the pressure of no, and this is the height of oil 173 feet, and we are to determine the corresponding height of water in meters. If this is 173 feet of oil, how many meters of water there will be to produce the same amount of pressure? No? So determine the equivalent height in meters of water. So for letter B, centimeters of mercury. So this is mercury. Okay. So the height of mercury is in centimeters. Okay. And that will produce the same amount of pressure. Okay. So how did I know my so these are the assumptions. How did I know that this is the illustration and this is the illustration? So this is 0.8 specific gravity. So the lower the specific gravity of the substance, the higher will be the height. The higher will be the pressure head. No? So since this is the specific gravity of this is 1, okay? So this is expected to be lower than the height of oil. The specific gravity of mercury is 13.6, and this is expected to be to be the lowest, no, among the three in terms of pressure head, no, lowest pressure head that will produce the same amount of pressure, no. So that's the reason, because of their specific gravity. So if their specific gravity is large, no, the corresponding pressure head will be low, no? Will be small, no? So in this case, for letter A, solution to the problem, recall the formula that the height of liquid 2 can be obtained by multiplying the specific gravity of substance 1 to height of substance 1 over specific gravity of substance 2. So we have here oil. Specific gravity of oil for liquid 1, for liquid 1 height, liquid 1 pressure head, H sub O, all over specific gravity of water at 4 degrees Celsius. So again, the assumption is that the temperature of water is at 4 degrees Celsius, so that it will be exactly 1. So we have now 0.80 times 173 feet over 1. So converting that to meter, for every foot, 1 meter. So that is now 42.2 meters. So in here we have oil, and recall that the height is equals to the specific gravity of liquid 1 times the height over specific gravity of liquid 2. Okay? Then the height of mercury, no? So we have specific gravity of oil times height of oil over specific gravity of mercury. And we will obtain, so we have 0.80 specific gravity of mercury, no? The specific gravity of oil, 0.80, HO, 173 feet, okay? Then a specific gravity of mercury is 13.6. Okay, so multiply that by 30.48. So take note that for every foot, there will be 30.48 centimeters. 1 foot is 30.48 centimeters. Okay, so this will now be converted to 310 centimeters. So this is the corresponding height of mercury to produce the same pressure with the pressure head of 173 feet of oil. So that is only considered 310 centimeters of mercury. Okay, so we have here liquid pressure head in terms of water pressure head. So recall that if we are to convert uh, pressure head of liquid 1 to pressure head of liquid 2, we use this formula. No? Pressure head of liquid 1 is converted to pressure head of liquid 2. No? So if the pressure head of liquid 2 is water at 4 degrees Celsius, so the height of water at 4 degrees Celsius is simply Sg1H1 all over Sg water at 4 degrees Celsius. Now, Sg water at 4 degrees Celsius is 1. So therefore, this will now be simplified that the height of water at 4 degrees Celsius is simply the specific gravity of a certain substance times the height of that substance, no? The height of that liquid. Okay? So that's the simple formula, no? You just multiply the specific gravity of a substance to its height, no? So that will now be converted to height of water at 4 degrees Celsius. Okay, so that ends my presentation. So I hope you get it. Good day, everyone.